This is part 1 of my lecture on stellar evolution. I'll describe how stars are born, how they die, and what they leave behind. Stars are born in cold, dusty nebulae. A nebula is just a cloud. Galaxies contain different types of gas clouds. For one of them to form a star, it has to be cold. Here's where dust comes in. Dust blocks out the light from nearby stars, allowing a cloud to cool. It becomes cold enough for atoms to stick together to form molecules. The most common molecule in the universe is hydrogen 2, which is just two hydrogens bonded together. But molecular clouds also contain helium, which generally doesn't stick to other atoms, and small quantities of other molecules like water and carbon monoxide. Then gravity causes the cloud to contract. Some of the small, dark clumps in the Carina Nebula shown here are in the process of contracting to form stars. In other parts of the nebula, stars must have already turned on, causing the surrounding regions to glow. As a large molecular cloud starts to contract, it can break up into dozens or hundreds of fragments. Each of these will then collapse. More than 99% of the mass eventually ends up at the center to form one or more stars. Until a star begins fusing hydrogen, it's called a protostar. The leftover material forms a disk around the protostar. At some point, the protostar begins ejecting a wind which escapes above and below the disk, and therefore looks like jets being emitted from the poles of the protostar. When the temperature at the core of the protostar hits 10 million Kelvin, hydrogen fusion begins. The protostar has now become a star. The energy produced in fusion replenishes what's lost because of the stellar wind. So the star stops contracting, and we have a genuine main sequence star. Meanwhile, planets can form in the disk. Eventually, the stellar wind clears away the gas and the dust left in the disk. What I've presented so far is theory. We can't directly see a cloud fragment, collapse, and turn into a disk and then a star. The entire process can take tens of millions of years. What we can see is snapshots of the different stages. On large scales are the famous nebulae, like the Carina Nebula, Orion Nebula, and Eagle Nebula, where hundreds or thousands of stars are forming. If we zoom way in on one of the dusty clumps in these nebulae, we sometimes see a disk and a jet. If we take images of one of these over several years, we can see the disk spin and the jets change in appearance. Here are some more disks around stars that are still forming. And here are two images along with models that show how they might look if we could see them more clearly. The light from the stars have been blocked out with a mask so we can see the disks around them. A main sequence star is one of the most stable objects in the universe. It will remain largely unchanged as long as it has hydrogen available in its core, which it will slowly fuse into helium. For a star that's as massive as the Sun, the main sequence lifetime is 10 billion years. For the most massive stars, it's just a few million years, and for the least massive stars, it can be up to 1 trillion years. When the Sun was born 4.5 billion years ago, it was around 90% hydrogen, and most of the rest was helium. The composition of the outer parts hasn't changed at all since then. But in the core, hydrogen nuclei have been fused together to make helium. 5.5 billion years from now, the core will be all helium, so fusion will stop. All this time, the energy released from fusion was helping to keep the Sun supported against gravitational collapse. The Sun is currently in equilibrium, which means the inward force of gravity is perfectly balanced by the outward push of gas pressure and nuclear pressure, which is basically the energy from the photons and neutrinos escaping from the core. Gravity depends on mass. Gas pressure depends on temperature. Neither of these things is going to change the instant nuclear fusion ends, since the mass and the temperature don't instantly change. But there's no longer any nuclear pressure. Until then, it was nuclear pressure plus gas pressure, which equaled gravity. Now that there's no nuclear pressure, gravity wins. The net force is directed towards the center of the sun, and so the core contracts. If you compress a gas, it will heat up. Previously, the outer boundary of the core had a temperature of 10 million Kelvin. Now it's much hotter. Some of that heat is transferred to the outer regions. So there's now a region outside of the core, which is made of hydrogen, but is more than 10 million Kelvin. So fusion begins there. There's no fusion happening in the core, but there's fusion in a shell outside the core. With fusion, there's nuclear pressure. Also, with the increase in interior temperature comes increased gas pressure. This means gas pressure plus nuclear pressure is now greater than gravity. This causes the outer regions to expand. The sun is going to turn into a red giant. You probably already knew that the sun will eventually turn into a red giant. What you probably didn't know is that what initiates the expansion of the outer regions is actually the contraction of the inner region. When the temperature of the inner core hits 100 million Kelvin, helium can fuse together to make carbon. This never happens when the lowest mass stars die, but it will happen in the sun. A small amount of the carbon that has been made will even combine with helium to make oxygen. At this time, the sun's interior is a bit like an onion. You peel away one layer and you get another one. The innermost part of the core has been turned into carbon and oxygen. The sun never becomes hot enough to produce any other elements. Just outside this layer, helium is still getting turned into carbon. Outside of this, you have helium that's not hot enough to fuse together. Then you have hydrogen being turned into helium, and finally the outer region, which is all hydrogen. You don't have to remember all of this. What I would like you to know is that eventually, when there's no longer any type of fusion, the sun will have an inner core made of carbon, an outer core made of helium, and a huge envelope made of hydrogen. The core has become so small and the outer envelope has become so large that the two become decoupled. The gravity of the core can no longer hold on to the outer region. The star ejects its outer layers. There is a terribly confusing term for this. Astronomers call this a planetary nebula. We now know it has nothing to do with planets, but when astronomers first discovered these type of objects, they thought these must be places where planets are forming. Once a name sticks, it's hard to change it. If you find that unacceptable, you can join me in referring to these by a different name. How about dying sun nebulae or sun's last breath? I have zero influence on the astronomical community, but maybe one of you will succeed in getting rid of the term planetary nebula. Here are 4 dying sun nebulae. The one on the bottom right is the youngest. The outer regions are being ejected. The one at the bottom left is further along. The parts that are being ejected now are moving faster and therefore colliding with the parts that were ejected earlier. In a few thousand years, this nebula might look like the one above it does now. By then, though, the one at the top left would have faded away. The one at the top right happened when a star died which had a close companion. Some of the gas ejected from the star ended up forming a disk around the companion, and as more layers were ejected, they escaped above and below the disk. The disk lies deep inside and is oriented like this, and the material is being ejected above and below the disk, like this. In summary, a low-mass star like the Sun turns into a red giant after it runs out of hydrogen in its core. Its core contracts while its outer regions expand. Then the outer regions are completely blown off to make what I call a dying sun nebula and all other astronomers call a planetary nebula. The dense core of the star, which is now made of helium and possibly also carbon and other elements, is left behind. This is what we call a white dwarf. High-mass stars start off just like low-mass stars. After the core runs out of hydrogen, It shrinks and gets hotter. Hydrogen is fused into helium in a shell outside of the core. As the core continues to shrink, it fuses helium into carbon, but it doesn't stop there. It can make heavier elements like oxygen, neon, silicon, sulfur, and iron. Meanwhile, the outer parts keep expanding. We call this a red supergiant. You don't have to know all the details. What I want you to know is that something happens when the innermost part of the core has been turned into iron. Here is one of the most important charts in nuclear physics. It shows the binding energy for different nuclei. This is the minimum energy required to separate the nucleus. The higher the binding energy, the harder it is to turn this nucleus into a different nucleus. If you move up on this chart, you get energy out. In the Sun now, 4 hydrogen-1 nuclei are turned into 1 helium-4 nucleus. Notice that hydrogen-1 is way down here, while helium-4 is way up here. So a tremendous amount of energy is released when hydrogen-1 is turned into helium-4. The next element after helium is lithium. There's a drop there. This means if you turn helium into lithium, you don't get more energy out than you put in. The next element that will give you more energy than you put in is carbon. That's why carbon is the next element that's made in dying stars after helium. Then oxygen and a few other elements will be made all the way to iron. Once you get to iron, there's no way you can get more energy out than you put in. So far, I've been talking about fusion, which is the combining of light elements to make heavy elements. The other way to get energy out is to take something heavy like uranium and split it to make 2 lighter elements. That's called fission. The energy released in fission is far less than what's released when hydrogen is turned into helium. But fission also ends when you get to iron. So fusion stops in the innermost part of the core of a high-mass star once it's made of iron. Once again, gravity overpowers pressure. The core shrinks further. The protons and neutrons in the iron core fuse together to make neutrons. This releases a huge amount of energy in the form of neutrinos. To a neutrino, most places in the universe, including the interior of a star or a planet, look completely empty. That's why neutrinos go right through the Sun and the Earth. But the core of a dying high-mass star is so dense that even neutrinos interact with them. A huge amount of energy is released, which completely rips apart the outer parts of the star. Astronomers call this a supernova. More precisely, this is a type 2 supernova. Here is what's left of a star that was seen exploding in the year 1054. It actually happened 6,500 years earlier, but that's when the light hit the Earth. Astronomers in China described a star that suddenly appeared and remained brighter than all the other stars in the night sky for months. Now, the debris is 6 light years wide. The tangled bright lines you see in this image are from shock waves, which are produced when matter travels faster than the speed of sound. The only supernova that could be seen with the naked eye during the last few centuries was 1987A. It's not in the Milky Way, but in one of our companion galaxies, the Large Magellanic Cloud. Composite images show how the debris has been expanding over time. Here are supernovae seen in other galaxies. For a day or two, they shine brighter than all the other stars in that galaxy put together. Notice that some of these don't even appear to lie inside a galaxy that we can see. The rest of the galaxy, or that part of the galaxy, is so faint that we don't see it. In summary, high-mass stars start off just like low-mass stars, but end up making heavier elements in the core. Meanwhile, the outer parts expand into a red supergiant. Once the inner core is made of iron, it collapses. Its protons and neutrons combine together to make neutrons, and this releases a burst of neutrinos. The outer parts of the star are completely ripped apart. We call this a supernova. The core that remains is either a neutron star or a black hole, which I'll get to later.